Alright, welcome back to particle physics and the standard model. This is lecture 25 and last time we had just rounded up our quantum field theoretical treatment of spin-1 states, right. We saw how to embed spin-1 particle states into Lorentz 4 vectors, and we saw how to cleverly get rid of the correct degrees of freedom such that we get either 3 propagating degrees of freedom for massive spin-1 states or 2 degrees of freedom, the polarizations, the transverse polarizations for a massless spin-1 state such as the photon or the gluon and so on, right. So, what is left to do now? We have done spin 0 and described by the Klein-Gordon equation and the relevant Lagrangian, spin 1, right. Let me just write that down. Spin 0 was the Klein-Gordon equation, spin 1 was Proca, right, for massive states, and these are all free theories, okay, no interactions. And what is it for the massless one? We can just call it the Maxwell Lagrangian if you want, because that is what gives rise to Maxwell's equations, right. So, what is left? Spin half. This is where the fun really begins, okay. Probably the most important representation of the Lorentz group, spin half described with spinors, and what is this equation? It is the Dirac equation, that is the equation of motion for which we are going to construct a Lagrangian in this lecture, alright. Now, let me give you some historic background for this equation, because there is a lot of confusion about what this is. Dirac himself was very confused about it, okay. So, let me give you some background having learnt what we have learnt so far in QFT, so that we can set some things right away, okay, as far as physical intuition goes. In the first place, let me just say that Dirac he guessed the equation, okay, unlike the Klein-Gordon equation which we derived right from some principles involving Lorentz invariance and so on, and unlike Maxwell's equations which we had from earlier, right, and even the Proca equation of motion, Dirac literally guessed, okay, it was a leap of genius, I should say, okay, guessed the equation of motion for spinors, okay, and he got it right, okay, up to a point basically, because what he also wanted to do, unfortunately, okay, I believe this was in 1926, what he also wanted to do was generalize the Schrodinger equation only. Remember, we tried to generalize the Schrodinger equation when we wrote down the Klein-Gordon equation to relativity, right, to a relativistic situation. So, that is what his aim was also, okay. So, that meant he also interpreted the field, right, whatever he wrote down, as a wave function, and this is what led him to a lot of trouble. Why is that? Because remember, when you do a mode expansion of this, even in the Klein-Gordon case, right, if you do a mode expansion, you got states that looked like negative energy states, right. Right. And if you go back to the lecture, one of the first lectures on the Klein-Gordon equation, how did we interpret these negative energy states? We did not say these were particles with actually negative energy, okay, because this is always true, okay, it is always positive, there is no doubt about that. What we did instead was the operator that was sitting in front of the negative energy, the state that looked like a negative energy state, the plane wave that looked like a negative energy, we took that operator and said this operator corresponds to creating an antiparticle or destroying an antiparticle and so on. right. Remember we wrote a mode expansion with I am writing 4 vector notation. We had a term like this, right. So, I can put this as a function of k, this is also a function of k e power minus kx, right. And then when you do the expansion, this looks like a negative energy state, except it is not, it is a positive energy state only, it just corresponds to anti-particle creation. This is something Dirac did not completely understand, because he was also thinking of this as a wave function, okay. And that is what, this is what led him to propose a very famous concept called the Dirac sea. What is the Dirac sea? He said that actually the universe at every point, right, contains negative energy states also. So, let us call this 0 energy, okay. And then he said because these are fermions, all the negative energy states, okay, these are all constitute E less than 0, okay. He said all these are already filled because they are after all like a Fermi sea, right, at every point in space, okay. And then whatever electrons we do see now, so let me probably draw that in red, okay, they are the ones that happen to be positive energy, okay. And he said then he interpreted the existence of antiparticles as I am going to deliberately erase something here using a small eraser. If one of these energy states, okay, jumps over, gets excited basically, okay, then you created a hole, right. So, this hole is what we infer as antiparticles, okay. At some point he also said maybe the proton is the antiparticle of the electron because it has the opposite charge, but of course he conveniently forgot that the proton mass is much heavier than about 1000 times heavier than an electron. So, that was wrong, but nevertheless even positrons according to him should be inferred as holes in the Dirac sea. This is the Dirac sea basically, this negative energy filled up states, okay. Of course, this runs into a lot of problems. This is unbounded from below, right. You can't have interactions, you can't write down any serious theory of interactions of electrons with photons, etc., etc., etc. This runs into a lot of problems. So, it is worthwhile writing down that this is completely crazy, okay. Nobody should take this seriously. There are some nice science fiction stories based on this, but nothing more, okay. This is not the physical picture of the world, although Dirac never admitted to it until the very end, okay. Today of course we are much more enlightened, we do know how to interpret the negative energy states. They are once again not wave functions, okay. Again let me just write it, it's worth remembering these things. These are not wave functions, but operators, a combination of operators in fact, right, creation and annihilation operators, very good, okay. But how did he guess this? That is really what his real contribution was, okay. Giving the equation itself, it took a genius like Dirac to get us here, okay. So, what did he do here to get the Dirac equation? Let us follow through his steps and let us derive the Dirac equation ourselves, okay. Again remember this relativistic equation, right, of course in field space is what we are trying to get, but in a but including quantum mechanics, correct. So, if you just kept this, the squared version of this, right, the squared version like this in field space, that is literally Klein-Gordon equation, right. That is literally what we have been writing down all this while. The client got an equation. So, his idea was, why do we want to keep the squared version? The real idea is to only put space and time derivatives on the same footing. That is the main thing here, right. So, instead of just using the squared version, he asked if it is possible to factorize this, okay, and get a linear version of this, not a quadratic version like here. That is what he sought to do, okay. Let us see if we can do this. Can we linearize this, right? There is a way in which you can do this. Let us take a very simple case, and then I can show you how easy it is, how easy it looks, okay. Take the case of, I am going to go to a frame where I set the 3 vector to 0, okay. Then what happens? In the metric that I use, at least what happens? Then I have P naught squared minus m squared equal to 0. So, P naught is plus or minus m, okay, easy peasy, right. Right now it looks easy peasy, okay. But what about the general case, right? What if I want to keep it Lorentz invariant? So, generally I still have this, right, but here is something I can do. Let me see if I can find a linearized version like this. I am going to use the most generic coefficients I can think of, okay. So, I am going to put lambda k p k here to denote that repeating indices are summed over, okay, like in the Einstein convention, okay, plus some zeta m, and then sorry, let us say lambda, I meant gamma, okay, gamma k, and then similarly I have a gamma lambda p lambda minus zeta m equal to 0. Agreed? All I have done is just factorize this equation, okay. Okay, let us see if this works out, okay. Of course, I can now expand this. This gives me gamma k, gamma lambda, pk, p lambda minus zeta squared m squared equals 0. Now, I want this equation to look like this equation now, right. So, what does that mean? It means I need these coefficients such that gamma k, gamma lambda, pk, p lambda to be equal to p mu, right. And what else do I need? I need zeta squared to be 1, correct. But there are other things I also need, right. I need the cross terms to vanish basically, right. For example, I need, let us take this combination, this and this, okay. So, I need this to vanish, correct. I need this to vanish, and so on, right. How many cross terms are there? You can actually count and you will see that there are actually 6 cross terms, okay. In other words, you can fix 4 coordinate terms. So, why are there 6? Because what does k and lambda run over? They run over 0, 1, 2, 3, right, because I still want everything to be Lorentz covariant and so on. So, k runs over 0, 1, 2, 3, right, they better. Similarly, lambda also, So there are 4 gammas, there are 4 kinds of gammas basically, that is what it means, right. If that is the case, you can do the counting and see that there are 6 cross terms. Okay. See, that is impossible now, right, because the number of unknowns that I have to fix seem to be much smaller than the number of constraints that I have in the system, right. So, for example, I can pick gamma 0 to be plus or minus 1, right, so that I get a p0 squared is, I get, if it is 0 gamma 0 gamma 0, if it is that, then that is a 1. So, I get p0 squared equal to p0 squared. Then I have to pick gamma 1, gamma 2, gamma 3, all of this I can pick either plus or minus I then, right. Remember, in my metric I use this metric. So, the spatial components pick up a minus 1, so I must have a plus or minus I, so I have a minus 1 out here in front, right. So, this is one solution where I satisfy this condition, but then that does not give me this condition, right. So, after fixing the quadratic conditions, 6 cross terms cannot be eliminated. So, what should we do then? This program seems to have failed right at the outset, right. So, what should we be doing? So, this is where Dirac's genius came. He said we should not think of the gammas and the zeta as numbers, let us imagine that they are actually matrices. Okay. Let us call the gammas and zeta matrices, okay, and then let us see if we can work out the properties of these matrices, okay. Right away you see that these conditions now, right, could now be translated as, in matrix language, I can now write gamma 0 squared is what? It is the identity matrix. So, I do not yet know the dimensionality of this matrix, okay, but at least I can guess that it is an identity matrix. Similarly, this condition for the other gammas should give me what? That gamma 1 or gamma 2 or gamma 3 squared gives me minus the identity, okay. Then can I do something about the cross terms? Now I can, right, because the cross terms, if you notice, they come like this, right. So, there is a, whenever I have a gamma mu, by the way, by cross terms I do not mean just the cross terms between the m and the pk, I actually meant cross terms like lambda k, gamma k, gamma lambda and so on. The cross terms in the momentum, okay, those are the more important ones that we are thinking about here, okay. Is that clear? These cross terms. So, let me just mark them in green, these kinds of cross terms, okay. So, now notice that because of the way the indices are written, when I have a gamma mu gamma nu, I will also pick up a gamma nu gamma mu, right, because the k, the k goes from 0 1 2 3, lambda goes from 0 1 2 3. To take an example, if I have a 0 here and a 1 here, I will always end up in the expansion, I will end up with a 1 here and a 0 here also. So, in short, I can just write mu nu nu mu in that order, okay. Now, this is the cross term we want to eliminate. This is actually what leads to the 6 cross terms, okay, not this, okay. So, this is when if mu is not equal to nu. Very good. Agreed? So this might look a little weird now, right, because mu and nu you are used to seeing as some Lorentz index acting on some 4 vector, either a contravariant index or a covariant index, but now we are labeling these matrices themselves as with a mu and a nu to correspond with the mu and the nu in some vector or spinor and so on. Okay, so that is a slightly odd thing here, but let us go with it. Okay, it is just a label to show that each of the gammas is different. Okay, gamma 0, gamma 1, they are all different. Okay, then can I now condense these conditions into a single equation? You can think about it, but I am going to write the answer. It is very simple. It is just that gamma mu, gamma nu, when I put them in an anti-commutator, I get 2g mu nu. Okay, that is the condition that these matrices need to satisfy. And of course, there is another one which I can just set to 1, the zeta. So we will not talk about the zeta much after this. Okay. So this again you can easily work out what is the smallest set of matrices, set of gammas. Let me just write matrices that would work for this condition to work out. Could it be a 2 by 2 matrix or a 3 by 3 matrix? No, not really. You can work this out. Okay, take just 2 by 2 matrices and see if you can construct, take the Pauli matrices. Okay, you might imagine the Pauli matrices come into the picture and see if all these conditions can be satisfied. You will find that no, that it does not work that way. Okay. After all, this is all tied up with the fact that we are working in 4 dimensions, right, 1 plus 3 dimensions. So all of these come together and you see that the smallest set that works is 4 by 4. Okay. And this is the only condition that they need to satisfy, and that means you have a non-unique sets of the gamma matrices that satisfy these conditions. Okay. In other words, there are many bases. Okay. So when I say set, I mean there are many bases in which you can work to satisfy these conditions. Okay. So there are, I think, 3 or 4 kinds of bases. You can go look this up in any number of textbooks or in Wikipedia for the gamma matrices. But we will use what is called the Weil basis. Okay. So let me write. So there are 2 names for these: Dirac matrices or just gamma matrices. And in the Weil basis, which is my favorite basis, gamma 0 is 0, that is not a 1, that is an identity. And if I write it this way, you have to remember that this is a 2 cross 2, this is a 2 cross 2 identity matrix, and this is a 2 cross 2 identity matrix. So what I have done is write this in a block diagonal form. Okay. So that this is still a 4 cross 4 matrix. Okay. What about the other gammas? The gamma i's, now I can write in terms of, what am I writing here? These are the Pauli matrices. Again you see Pauli matrices are 2 by 2, and so the gamma matrix is a 4 by 4 matrix. Okay. So this is the basis that we are going to use. This is the basis in which you can most easily understand what are known as right handed fields and left handed fields and so on, which we will explore, etc., etc. Okay. This is not the basis that Griffiths use. Okay, if you have been following Griffiths as the textbook for this course, he uses the basis that is slightly confusingly called the Dirac basis. I believe this is the basis that Dirac himself had used in the beginning. Okay. And this is not so friendly to how I will treat spinors in this course, the Lorentz spinors. Okay. Now in that basis, I am just going to write that down for completeness sake. Gamma 0 is like this. Okay. This is very confusing for me at least. Everything is consistent. Okay. All these bases actually satisfy the anti-commutation relations we want. It is just a question of taste, convenience, what you really want to calculate and so on. And the gamma i's are still the same. Okay. All right. So a little exercise for you would be to go and check or derive. Okay, derive is better than check the other bases. See for yourself what kinds of gamma matrices you can actually get. Okay, very good. Now that we have the properties of gamma matrices, we can finally write down the actual equation of motion, right, because ultimately this was what Dirac was seeking, something like this, right, one of these linearized equations of motion, correct. So that is simply at this point an I. Why is that? Because p squared is minus partial squared, right. So if I am taking the linear version of that, then I will put an I d I partial mu, right. But that is not all. I want the Lorentz index to contract with something, and now that something, which is where this might look weird when you see the first time, is the gamma matrix itself. Okay. But it is a very valid contraction. Okay, even though it is a matrix, this is exactly how you get a Lorentz invariant theory for spinors. And of course, the mass is a mass. I could have picked either the plus or the minus among these two possibilities. For now I am just picking the minus, okay, it is a convention. And of course, this is acting on a field, not, let me remind you, on a wave function. This is literally the field that describes the spinor operator, spinor quantum field, okay, and that is the Dirac equation. Okay. So let me wrap up this lecture by noting three interesting things in this treatment. Okay, three interesting things in this equation and how we set about writing down the Dirac matrices. Okay. So three things to note. First, right, what is should we write this psi as a number or a matrix? Of course, we have to write it as a matrix, right. Why? Because we are multiplying it with what? A gamma matrix, right. So this should also be a matrix, and in particular it is a 4 element column matrix. Agreed? unlike the Klein-Gordon field, which was just a number, and unlike the 4 vector, right, which is actually a 4 vector after all, this is something different. This you represent with just a 4 element column matrix, right, and that would mean that when I just wrote M here, I actually meant M times an identity sitting here, a 4 cross 4 identity matrix. Okay. Okay. Next, we see, we just noted that the Dirac matrices were composed of 2 by 2 blocks, right. That seemed a little strange, right, they are not very generic matrices, there is a nice pattern to this, correct, 2 by 2 blocks that seem to say something about spin because they are made of polymatrices, right. And remember also that when we were doing quantum mechanics, right, in quantum mechanics the spinners we used were 2 column matrices. Agreed? Now what I am going to tell you is that none of this is a coincidence, okay. They are all part of a large, very interesting structure. They come from a structure placed upon them by Lorentz invariance itself. Okay. And how this comes about, we are going to see in the upcoming lectures. Okay. So, in the next lecture we will solve the Dirac equation and we will gain more understanding of where this stands in the larger scheme of things. Okay. So, I will leave you here, see you in the next lecture. Thank you.